the switch reluctance motor. You see my initial slides that FRM motor, flux reversal motor, and these two are a similar structure, but switch reluctance motor, so we are not using any permanent magnets on this SRM, just it is like a conventional, but you can see here. So here earlier if you see my FRM motor, FRM, that is 2x3 flux reversal motor, but whereas 2x3 means 2 stator poles and 3 rotor teeth, but here the rotor teeth I think 4x6. So number of poles are more and rotor teeth are also higher here. This is 4x6 I think. So another structure what I consider is 4x6 for two-phase motors, because our target is how to eliminate our magnet-less motor. So I can say this is a simple word. So as an engineer or as a researcher, you need to start working on magnet-less motor. So as a result of that, I am searching for different topologies to work on this to achieve that magnet-less motor. So I have considered like 4x6 SRM motor, switch reluctance motor. It is one of the best alternative for two-wheeler applications compared to BLDC motor as well as permanent magnetic synchronous motor. If you see the BLDC motor, again we are using the permanent magnets, but here there is no permanent magnets. So it is already nowadays we are also recommending, and we have already tested in the ANSYS also this 4x6, and industrial application is also started for this. So I have considered like two-phase application, three-phase application. For two-phase applications, 4x6 motors configuration I am using, and for three-phase applications 6x4, like 6 stator poles and 4 rotor teeth, and also 6x8, like also 6 stator poles and 8 rotor teeth. So the thing is, this flux reversal motor, FRM as well as switch reluctance motor, the primary thing is there is no winding on the rotor. It is just like as a teeth. It's like aluminum like steel blade. So if there is no winding on the rotor, so definitely it is easy to, the movement will be high. The torque will be, production will be more. The torque density will be high. So that's why I have considered these different parameters for torque value, current value, and torque ripple. And the thing is, again, when you are going for the speed application, again the speed is also thing is 10 RPM, how much torque we are getting. For 200 RPM, 100 RPM, how much for 200 RPM and 300 RPM. So like this I have considered, and common design parameters for two-phase as well as three-phase also. The rated current is 60 amperes, and these are the parameters also what I have considered. So like 4x6 two-phase motor, and 6x4 and 6x8 are the three-phase motor. This is the structure. You kindly see in the stator I am not using any pole shoe here, and there is no permanent magnets. It is a completely magnetless motor. And this is also another thing what I did is, but I have done some work related to what I proposed in the rotor techniques, rotor torque cogging techniques. You see here in the stator, the rotor technique, some of the cases rotor pole shoe, you can see this, I am extending the arc of the rotor. So it means I need to reduce the cogging torque and giving the highest torque value. So this is a special arrangement what we did in the simulation, and then we achieved also, and we are getting, I have considered like 6 different arrangements of this position A, position B, position, all these arrangements I have done with the torque profiles, and then I have compared with these structures by arranging this type of rotor, I think. And then you can see the position of the electrical angle with respect to torque. So when I am getting 60 degrees of rotor theta angle, and from 0 degrees to 360 degrees when I am moving, for different cases, like this is one type of structure. So like 6 rotor stator structures I have considered, and then this is where I consider. And also this is the algorithm what we proposed to achieve the highest phase excitation condition. So because now we are using 4 excitation. So every time that's why we call it as a switch reluctance. We have to switch from one excitation to another excitation. Like 4 excitations I have considered. When the angle is, what I observed here is from this graph. So in between 130 degrees to around less than 220 degrees, I am getting the maximum torque, I think. From this profile, I observed that when the rotation is from 160 degrees or 130 degrees to 230 degrees or 220 degrees, I am getting maximum torque. So that's why I have designed the algorithm that the torque angle, that is electrical angle, is greater than or equal to 130 degrees to less than or equal to 180 degrees. So up to like this I have given for each phase. So for example, for phase A excitation like this angle, and phase B excitation like 180 degrees to 310 degrees, and phase B and phase A again. So I have divided like this from the particular position. I think I have again zoomed this. You can see the position 1, position 2 and position 3. So this is my control algorithm what I have adapted, and then we are executing this. And coming to this switch reluctance motor, this is the general what is aligned position and aligned position and intermediate position. So what I means aligned position is the rotor pole axis coincidence with the excitation of the stator. So then we call it as a aligned position. Unaligned position is it is different, like stator pole axis along with the interpole axis we call it as an unaligned position. So in between aligned and unaligned we call it as a intermediate position. These are the three positions are there, and these are the simple fundamental mathematical equations. The power of the SRM motor is like energy losses and also energy stored in the magnetic field, and then this is the mechanical power developed in this. And you can see this whenever the aligned position and unaligned position, you see here this is my stator. So the stator having 6 pole and rotor having pole 4 pole teeth, I think. So I am seeing here, you see here this is the aligned position. Aligned means if the here you can see rotor as well as stator both are aligned here. At this position aligned position, and at this position is unaligned position. So then the variation of the inductance with respect to the rotor angle. So see here it is a minimum inductance is existing here. If it is a rotor is unaligned position, minimum inductance. If the rotor is aligned, then we are getting as a maximum position. So there is a mathematical calculation to design what is the width of the rotor slot and stator torque slip. We call it as a ratio. So that ratio is also there. Just it is a machine design parameters. All these terms will come under machine design parameters. So based on that, I have taken. You also see the motor torque when it comes to the aligned position in the middle of this aligned position. So it is increasing. So this is the motor current, and also it is also giving as a both acceleration as well as deacceleration is possible. So that's why what I adapted the same technique. So then you also see the motoring action and braking action, how it is possible. So this we call it as a motoring action, and then again it is a negative. When the torque is negative, we call it as a braking action is possible here. And also like the current chopping is also existing here. So this is the current chopping. So upper band as well as lower band. So based on this current chopping, we are controlling the excitations of each phase, I think. And then this is the topology I proposed, and I got funding from the ministry of this. What I did is when the electric vehicle is moving, so onboard charging of electric vehicle. So now plug-in hybrid electric vehicle. So this is one of the technique what I propose, onboard onboard charging technique. It will runs like PV as well as charging. Like this is the external source, external power supply, and internal PV on the top of the surface electric vehicle we are plating as a PV panels, and anyway battery bank is also there. So battery banks are also existing. So here this is the battery bank. So two batteries I am considering here. So this is my front end converter, and this is my asymmetrical converter. This converter will drive the SRM motor, and this converter will getting the supply from the different sources. I considered here, you can see this is the power flow. I told you there are three types of sources here. One is the battery, another one is directly supplied from the external source, and then another one is the panel. So I have proposed like 6 modes of operation. One is PV alone driving mode, another one is battery alone driving mode, third one is hybrid driving mode. So PV alone driving mode. So what PV alone driving mode? So in that case, junction J1 and J2 open and J3 is closed. So when I close this relay, so then it is only PV alone driving mode. Battery will not start. So like this, I have differentiated for motoring action as well as charging. So I have considered 2 types of modes of operation. One is motoring mode as well as charging mode. So the charging mode you can see. So directly if you connect here for charging mode, battery charging by PV, junction J1, J2, J3 are turned on, the battery will getting as a charge. So this type of system, if you see, In EV vehicles, now the gear mechanism is there, gear 1, gear 2, automatically it is switching. Automatically based on the state of battery, it will take from which source I have to take the energy, whether I have to take directly from the panel or maybe I have to take from the battery. If both the things are there, then my system will generate an alarm to go and connect your battery to the external supply. So this type of techniques I have considered from this only. This is the front end converter and then the asymmetrical converter. This asymmetrical converter will drive the SRM motor, and this converter will tells the state of battery condition, and then accordingly it will start. Why I am proposing this is, if you see here, the starting condition as well as in the starting condition, if electric vehicle is started, and I have considered like this, it is only PV and battery working together, because I need a highest starting torque. At the time of starting, I have the source of energy from battery as well as PV. So then the low speed running condition, when the vehicle is going with the low speed condition, only the battery is working. So you can see now the Tata Nexon, they are giving city mode, eco, like this. I have also introduced the same concept in my vehicle application. So when based on the speed condition and based on the starting condition and normal low and acceleration, when I am going with the hill station, then again PV as well as battery working together. High speed conditions also PV working. So when it is a de-acceleration, like when it is going the downfall, so then your battery is getting charged. So these are the 6 models I have considered, and we implemented same thing. And you see now the again another technologies at the front end. These technologies I think I don't want to discuss. The comparison of EV vehicles, these are not required, I think. So okay, we will go to this paper, I think. Yeah, this is the roadmap, EV adoption roadway in India. So how we are going, like this is started, National Electric Mobility Mission Plan has started in 2020. Again now it is started in 2017, first plan, and then again second plan has started here. So now this is the roadmap for to achieving 2030. So most of now, I don't want to emphasize much about this. And the forecast penetration of the curves for EV by vehicle categories like two-wheeler application, three-wheeler application, vehicle like transport vehicles. So like year-wise, financial year-wise, they are projecting by financial year 2030, 2030, most of the vehicles like three-wheelers are 90%, scooters are 75%, like buses are maybe 37%. Four-wheelers, like four-wheelers, we will achieve only 15% like this. So this is the way we have considered here. I have mentioned the same case. And the challenges faced by the EV industry in India, like battery charging infrastructure and high price, that is also another case, and limited options to the lower mileages, and also the dependency on imports. I told you, so we are getting a lot of material importing, we are importing that. High dependency on impact due to the lithium ion is also on battery technology also we are getting. So other chemical used for the battery manufacturing is also things. This is the case. And then interaction. And one more paper is there. Can I open that paper?
Any question answers from the
Any please.
The switch reluctance motor, our students have worked. So what are the challenges as of now? You already mentioned.
Yeah.
Torque ripple is the one major challenge.
Yeah. For switch reluctance motor, the initial position of the rotor. So because aligned position and aligned position, because I am working on sensorless control of switch reluctance motor. So anyway, the switch reluctance motor cogging torque are less, I think that's not an issue, and we are not using the magnetless motor. The thing is, the initial position of the rotor, when you know the initial position of the rotor, so based on that initial position of the rotor, you are giving excitation to the stator coil. So whenever you are giving excitation to the stator coil, so then the magnetic field will develop, then that rotor will be rotating accordingly. So if the both the poles, stator pole as well as rotor teeth are aligned, so then once it is aligned, then you switch to phase A to phase B excitation. So that's the major issue. So how to identify the initial position of the rotor? So for the initial position of the rotor identification, they proposed sensorless control techniques. There are some signal injection method. So signal injection method, what it will tell is, initially you give as a DC ramp signal. to the stator. So then we will find out which whether we are getting any rotation. So once there is a rotation, means the poles are not aligned. If there is no rotation, it means already your stator is already aligned with the rotor. So that's why there is no rotation. So the major challenging with the SRM motor is identification of initial position of the rotor. So that's we call it as a sensorless control technique. We cannot put a sensor inside the rotor by putting some hole and we can. So that's why we need to do some mathematical modeling, and then now people are working on sensorless control of SRM motors and sensorless control of permanent magnetic synchronous motor. Both are same, but there are extended Kalman filter method, signal injection method, incremental inductance method. So these are the methods which are existing and people are working on the same.
Efficiency point of view, sir, if you compare SRM efficiency is are poor, or what is the?
Yeah, efficiency is poor definitely, because I told you in one of my slide, it is not functioning. The bidirectional torque capabilities are not there. So that's why it has efficiency less. But see, one side you are targeting about magnetless motor. So my target is I want to run with a magnetless motor. But for application, you see, the speed of a SRM motor is 10,000 RPM. Minimum speed is 6,000 and maximum speed will be going up to 10,000 RPM. So if you need a higher speed application, you may go for SRM motor. For limited speed applications like what we have, so then you will go for permanent magnetic synchronous motor or BLDC motor. For high speed applications like aircraft application, now the aircraft application SRM motors we are using. Are you getting, sir, my point? So any questions, any other questions? Yes.
How exactly it is possible and what are the challenges? How exactly one can start?
Sir,
As a professor, you have started.
yeah, that will be a different talk, I think. I have faced a lot of struggles. It will not cover in like 5-10 minutes, I think. So there is so many like startup. See, as a professor, I have started as a non-executive director, mentor. I am not an executive director. So there is some other person who is not a government employee. But the initial thought process, propagative, everything is done by me only. I have done my patent, and then that patent is now converted to the technology transfer. That's why I have taken one of my student, and he is job seeking person, and then I have given every rights to that person by putting he is also in the inventor of the patent. So that's it is a there are so many phases, I think. It is not an easy, but it is a difficult task. So is any other question? I will discuss with you, not this part. Next, any questions? No. It is for magnetic levitation application, like electric locomotive application. If you see the rail application, locomotive application, they are using, not in our India, but in Netherlands and Denmark, they are using this magnetic levitation application. It's not related to EV. Why I mentioned here is that special electric motor. So that's why I have introduced here. Any other question?
In the linear motor, how will go to full pixel? That is rotating machine will take that equation. To find the full pixel. But in linear.
Yes, sir. For linear, and that's why I told you pole pitch, sir. Design point of view is same, sir. Pole pitch, coil span, everything is same. But when you see the induction motor equivalent circuit and this linear induction motor equivalent circuit, both are different. So you have to calculate the slip value, and here again we need to put it in the slip value. That's why when you talk about the linear induction motor, it is very difficult with respect to end effect and edge effect. And we consider the equivalent circuit parameter. Designing of equivalent circuit parameters is also one of the challenging factor. So when we submitted a paper to IEEE, it's now second review is going on. So we got how you design these parameters, you tell me, because we have taken from some standard reference paper, but now he is asking you change the excitation or you change some poles. So how I will do, because I am working on two-fold. So designing a electric motor is not like as a software. So hardware implementation, we need to, nowadays people are students are thinking that who will do the stampings. Even a technician is not coming to do that stampings and all. So that's why I only restricted for two phase. One of my BTech student and MTech student, they designed, I think. So definitely, sir, there is completely torque equation. There we call it as a torque. Here I call it as a thrust. I think it's a force. I think so. It's not a torque equation. It's a force equation. Anything, sir? Yes. The thing is magnetless. The first benefit is magnetless. Whenever you are getting magnetless, it means the highest speed. See, like if you go with BLDC motor, the speed constraint, it will go up to 500 RPM. But when you go with the SRM motor, you will get more than 1000. Initial speed is more than 1000 RPM. So the costly point of it is there. SRM motor is costly, but BLDC motor is less. That's why should we will go for two-wheel application with the highest starting torque. So I have mentioned that 4/6. Now SRM motors are using for washing machine application also. You see the speed of the washing machine. It is moving with more than 3000 RPM. Sometimes it is going with 1500 RPM, because normally if you take DC series motor or induction motor, it is running up to 1460 or 1500 RPM. But SRM motor, the speed of the motor minimum is, I told you, 6000 RPM. So nowadays this SRM motor are using for the washing machine applications also they are using. Any other questions?
Motor having a good fault tolerance. Yesterday we have some fault tolerance.
Acha.
SRM, BLDC, different converter side fault tolerance techniques. Few of them
Sir,
are there, but motor from
the best fault tolerance
fault
is
tolerance, because
permanent
fault tolerance will be there for every
permanent magnetic synchronous motor for EV application. Because why I am saying this fault tolerance is, if you see the exact torque production of BLDC motor, permanent magnetic synchronous motor, flux reversal motor, and switch reluctance motor, the permanent magnetic synchronous motor is a sinusoidal in nature. So that's why PMSM motor are no other motor is beating that motor. So that's the reason why people are already taking this motor for EV propulsion. They are already in the market also. You will not feel anything whether you are running with the fuel or whether you are running with the EV when you are especially driving a EV motor, especially because of this permanent magnet, smooth operation. Any other? Okay, any questions?
Now running AIDC motor in that different diameter wheels are used to transfer. But when diameter gets changes, peripheral speed will get changed.
Yes, sir, exactly.
By 60.
Yes, sir, yes, sir.
So at that time, how we can get a particular rotation at that end wheel?
Sir, see, whatever the speed you are getting in the motor shaft, it is not 100% transferred to the vehicle wheel, sir. So because there is a gear and transmission wheel mechanism is there. So definitely it depends upon the pitch factor. We call it as a, when you started in the electrical drives concept also, there is a like a gear ratio factor is there. It depends upon the gear ratio factor. It's not 100%. For example, you are getting 1000 RPM in the motor shaft, but when the wheel point of view, you are not getting 1000 RPM. Maybe it is less than that, 750 RPM. Because this gear mechanism transmission will taking the rest of the things. But if you make as a compact diameter, so that's the reason why when if you see in my slides also, I have considered the dimensions as well as length of the stack also. Especially SRM motor 4/6 I am designing in my lab recently. So stack length, diameter length, these are also playing a crucial role while designing the motor.
Running is better than this.
Outrun is a plug and play, because see, it's a hub type motors. We call it as a hub type motors, and it is very simple to purchase. Even 3000, if you pay 3000 rupees in the market, you will get it. That's yeah, that is like hybrid electric vehicle, onboard charging. Maybe you can use directly in the daytime, but see, the how much of intensity depends upon again irradiation and factors. So 12 volts I required, then again 12 volts we are converting to 200 above 230 volts. So then it is a converter, it depends upon the converter efficiency, converter how best you are doing. So nowadays what we are doing is, I am using, most of the people they are using boost converter there, but now integrated buck boost buck converter, IB cube converters are also using. So all these things are, even though the duty ratio is low, then you will get as a maximum output voltage. So that's why the different techniques, one of the researchers they are using the same concept with the IB cube converter, integrated buck boost buck converter. My student is also done, but he is not using that converter for the EV charging stations, but he is using for other purpose, I think. For universal voltage control he is using. It depends upon the converter only. Yeah, that will charge your battery. Any questions? And sir, you can see recently I have published this paper. It is maybe in the month of September only this published, and this is a performance evaluation of flux reversal mission with rare earth magnetic, rare earth as well as non-rare rare earth excitations for micro wind energy applications, sir. So here what I did is, you can see this is very simple. The cogging torque is another factor, and also I considered two types of missions. Mission A is rare earth magnetic material, mission B is a non-rare earth magnetic material. And then I have to check the temperature stability, temperature how much when I am giving the excitation, how much temperature is also changing. I have done the temperature risk analysis also up to 150 degrees. And then the cost saving also I have done like 47%. And also the torque density of mission B is only 54% that of. So these are the major factors I considered. Take as a rare earth magnetic material or non-rare earth magnetic material, you have to perform like temperature withstanding capabilities and flux density capabilities, torque capabilities. Okay, these are the things we have done. Then, so in that case, yeah, you see, I told in my presentation also cogging torque minimization methods. I consider only rotor side cogging torque minimization methods, but in the literature, stator side techniques are there and rotor side techniques. Stator side is magnet skewing, slot shifting, dummy slots. So these are the conventional techniques already there. But usually stator side techniques may take a it's expensive than rotor type techniques. So that's why magnet skewing. See, if you how you will do the magnets where you want to skew the magnet, so then the wastage of the material is also going. So instead of skewing the magnet, you can skew the rotor. The rotor is a steel material, then it is better. So that's why I have considered rotor side techniques. There are more than 7 methods, 8 methods are there in the rotor side techniques. That is rotor pairing, rotor pole pairing, chamfering technique, notching technique, skewing technique, magnet optimization technique, magnet pole arc technique, flux barriers. So these methods, but out of all these methods, I considered only rotor pole pairing, chamfering, and skewing techniques. These are the 3 methods I considered. And especially for this writing this particular paper, I considered rotor pole pairing as well as skewing technique. So how I did is I have also mentioned here. So this is mission motor A. You can see here. So this is my 6x8 pole FRM motor. So like 2-dimensional as well as 3-dimensional views of this. These are the permanent magnets I am keeping here. So the south pole and also south pole here, north pole, and these are the excitations I am giving to the stator coils. And then you also see the permanent magnets where I am keeping. So these are the permanent magnets and this is the rotor. You see here the key parameters for mission A and mission B. So this is important. Sir is also asking the diameter, length, stack length. So the stator outside the diameter and the magnet thickness is also important. Both the magnets are magnet thickness I have considered 3 mm and number of turns per coil. See, for any motor, the specifications are very, very important. And these specifications you have to strictly go with the specification. For example, one slot you are doing some thing and another slot you put in a different manner, then the synchronization will be the another problem. So that's why, so maybe in the simulation point of view, ANSYS model, if you do that's okay, but hardware implementation it is difficult. This paper is already communicated. Initially we communicated to IEEE industrial application, but they are saying that for industry you need to have a hardware, but hardware we have not done, but simulation only we did. So then we went to some other Q1 journal and then we got it. So these are the mission A and mission B fact. And then another thing is cogging torque elevations. So we did the cogging torque elevations also. And you see the moving position, the cogging torque comparison of this material. So mission A how much and mission B how much. So mission A peak to peak cogging torque is 4.530 and mission B is 2.920 because I am using for mission B mission A is a non-rare earth magnetic material and mission B is a rare earth magnetic material. And then again, we have also calculated the cogging torque estimation, the peak to peak cogging torque evolution by this formula. And then again, we calculated the generated mass of the various parts of the motor again. And then temperature effect also we considered. So that's why we included the temperature parameters, and torque also we considered here. And you see here the cogging torque for various skewing angles. So see, whatever the skewing angles we did for 5 degrees of skewing angle. If you see the skewing angle is, if it is a 5 degrees, then peak to peak torque. If it is a 10 degrees, again it is coming to 0.5, 15 degrees, and then 20 degrees. You can see the optimal cogging torque where I am getting is for 15 degrees of 0.14. And then moving position, this is again you can see that rotor skewing angle for different loads, I think for different on load condition with the transient condition also we have considered. But anyway, it is giving for 15 degrees I am getting optimal value. So that's why we considered as a 15 degrees here. And you can see here, this is the rotor pole pairing, 2-dimensional and as well as 3-dimensional rotor pole pairing. So these 21 degrees and 19 degrees we make as a one pair. And again, we are pairing adjacent opposite coils, I think. So this is the rotor pole pairing technique. And then again, you see no load flux linkages on the basis of proposed topology, no load basis of this topology with different speeds, 375 RPM. And I have considered basic mission A, basic mission B, and then we changed the mission A. Proposed mission A is like only this rotor pole pairing as well as skewing technique, and there's a proposed A mission and proposed B mission also we considered. So those are things. And then again we compared like 4 motors. One is base motor A, base motor B, and proposed motor A and proposed motor B, with different comparisons what we did, especially for cogging torque ripple minimization, cogging torque minimization. And torque ripples also, torque ripple graph. Not only the cogging torque, again we need to see the average torque. So that average torque also I have considered for 4 motors. So the basic motor as well as proposed missions I have compared here. And then we did some analysis, load and transient analysis and ripple analysis also. And this is also again for comparison of power as well as efficiency and phase currents. So for 4 motors like mission A basic motion, mission B, proposed A and proposed B motors also we considered. Like power comparison, efficiency comparison, current comparison, and then voltage regulation also we did. Terminal voltage versus voltage regulation for mission A at the speed of 375 RPM. We considered as a for wind speed applications 375 RPM is the base, so that's why we considered. Again, the efficiency versus rotor speed comparison for the base as well as this is also output power versus rotor mechanics. So these are all the simulations we did through the ANSYS only. And again, what we again considered is you see here cost analysis. We included again cost analysis here. You can see the performance comparison like cogging torque, average torque, reduction cogging torque, reduction ripple torque, and efficiency. So these are the 4 things, like 4 motors we considered and 5 parameters we considered. And also you see the copper cost is around USD per kg, 7 USD per kg. Rare earth magnetic material 126.6 USD per kg, and non-rare earth magnetic material 18.46 per kg, and steel laminations is 1 USD per kg. So this is the cost analysis also we considered. You see rare earth magnetic as well as non-rare earth magnetic material for USD per kg 18 USD per kg with non-rare earth magnetic, but rare earth magnetic, you see how much it is, 126. This is a higher cost, I think. So and then the steel, copper is also like 7, And this is the analysis we have done. Cost analysis also we did for permanent magnets, rotor, armature winding, stator, as well as total active, I think. Again, we also did the analysis with respect to power factor and permanent magnetic flux density also we did. So with respect to power factor at different temperature degrees Celsius. See why, when the temperature is also changes, so based on the temperature the power factor is changes. So that's the reason why we did this analysis, as the temperature is one parameter, and then with the temperature how this magnetic flux density is also changes. So this graph also we did, and we made some conclusion. You also see here the comparison of mass cost analysis also we considered for all three: mass of the stator core, mass of the magnets, rotor, mass of the copper, total mission cost, torque density, torque for mass. So all these more than 7 parameters we did, because whatever the parameter we considered based on the previous literature, we added something, and then we have done all these things. And then this is also what I told you, based on the temperature with respect to power factor, how it depends. Like temperature is like, I have considered different temperatures. So like minus 40 degrees temperature, the power factor is 0.86. Like minus 20 degrees temperature. Then we did analysis for different materials. So that's why we made a comparison with the flux density, temperature, as well as power factor. So, and these are the temperature we made as a recorded the demagnetization points indicated by flux densities, power factor of rare earth excitation. So these are the rare earth magnetic materials. The structure when temperature variation of minus 40 degrees to 150 degrees centigrade we considered. And this is the mass and cost analysis I have already mentioned. So more than 50 papers we considered for review literature. Then accordingly we did. And also this is another case. And this is the structure finally what we decided to present. This is for non-rare earth magnetic materials. For non-rare earth magnetic materials, if you see minus 40 degrees temperature, the power factor is 0.65. For rare earth magnetic materials, if minus 40 degrees, your power factor is 0.85. So when you know the power factor is near to unity, you will get as a less tariff. So that is also the quality of power. So these things also we did with respect to power, and these are the different positions what we considered and laminate. Now everything is ready. Only the thing is now I am purchasing material for the design, manufacturing, actual manufacturing, I think. And this is about the paper, I think. Yes, if you can, I will give this paper to the conference chair. Then you can go through this paper. But what my advice, I worked on control of motor, okay, and different sensorless controls and design of this motor. Now it is very, it's not an easy, but it is understandable. I can say you will understand what we are doing. If you know the ANSYS software, then it is very easy to write a paper. If you have if you design one motor, then you will publish at least one paper. This is what I can. I told even my BTech students also, they are interested to work on this. So because electrical engineering means a real time application. So that's why if those who are interested to do this particular area, you can contact me, then I will. Thank you. Sir, in finite element analysis, there is option is there, sir. In ANSYS, even converter is also there. If you purchase a complete version for research, everything is there. In ANSYS is not only for designing of motors, temperature analysis is there, thermal analysis is there, everything is there. There are different modules, I think, but you have to purchase. We have a licensed version. If you purchase the licensed version, in the licensed version it is there. Even if you have a student version, but student version you cannot design many things. Gotcha. Okay. Any questions? Okay. Thank you.
Thank you, Professor Chandrasekhar sir. It was a really insightful and a very deep session on motors.
Achha.
Okay. We missed many things on motor, but as you finally concluded, we have to start from once again scratch from materials. Okay, so that is the research what we want today because of the challenges what we are facing in rare earth materials.
Last two sessions we got not to be superficial.
So this is the second session.
First start with the bottom,
So,
not with
fundamentals, I think.
Fundamentals only. So that is the requirement today for Viksit Bharat. The starting from the scratch is the requirement. So I request Professor Amrendra to felicitate Professor Chandra Sekhar with a memento as a token of love and appreciation from the Central University of Karnataka.
Thank you, sir. I think my bag will be better. Thank you, sir.
Thank you, sir. Now we have some resource persons from Keysight Technologies. Our university has come up with one MOU with Keysight. They are supplying instruments, especially for EV applications. They are already installing in our campus. Okay, so they will just give 10 minutes introduction about their products and how they are useful for EV and their applications. Please.
So, hello everyone. Myself Prasad here. I'm an application engineer from Applied Real Tech Systems. So, we are the authorized channel partner for Keysight Technologies for Karnataka and Goa as a region. So, today my agenda is very simple and clear. As I see the topic here is integration of AI and ML in electronic mobility systems. So, today electronic mobility, I would say it's not just only related to a mechanical and electrical components. It's also electronics, it's also automation, it's also mechatronics involved. So, collectively, it is a together of multiple domains together to make a product to come out here. So, from we as a test and measurement partner from Keysight Technologies, what we offer to a solution, I will just give a quick go through here. The first thing product I would like to say is an oscilloscope where you get to decode your protocols and other things, which will be the primary reason to communicate between your DUTs. So like say the basic protocols like I2C, CAN, LIN, from that starting from the very basic protocol of communications till your USB and your RAM and your DDR RAM, all those things can be decoded in these oscilloscopes. So today with respect to this mobility, I will just cover certain products from what we offer as a solution here. Coming to the latest trend, which is EV. So everybody will be excited if somebody tells EV the word or somebody is telling like they are going to work on some EV. First thing what comes to my mind when somebody say EV or anything with respect to electronics and with respect to thing is battery. Battery is the first thing which comes to my mind. Primarily now we are procuring batteries from the other countries where they are just supplying the battery and we are just integrating here. But we have a solution here which is called the battery tester. Yeah, this is this system. This is called a battery emulator. So this is basically a power supply come an electronic load, and this is not only that. So this integrates with the pathway software where you can actually define the size of your battery. Like say, but the only constraint here is it should be less than this 200 watt capacity. The capacity of this power supply and come load is basically 200 watt. So if you are going to design and you are going to test the repeatability of your battery, which can be done here basically with this software, with this pathway software that can be done here. So what this does is it's just battery profiling. So how fast or how quick your system drains, how does it respond to your sudden rises and sudden falls. Those things can be done here with this software. This is one solution from our end to battery. And one more thing I would like to cover is basically with mobility is EMI/MC. So if we are going into mobility, we are directly prone to emissions, where we should be knowing our EMI/MC and other things. For that, we have a solution with spectrum analyzer and signal generator. But primary thing with EMI/MC is where you are going to do and what you are going to do. Either you are going to do a CE or an RE, a conducted emission or a radiated emission. Primarily in automotive things, we will be doing a conducted emission only, because it's not just, we are not using any antenna to transmit. We are directly transmitting through our boards. So that you will be requiring a spectrum analyzer for a pre-scan requirement that we have as a solution, and with a EMC probe, so which is called a closed field probe. Thus we offer as a solution, but that is a limit. There is a limitation for that probe, which is only up to 3 megahertz. But that is a passive kind of a measurement. So any probes of any make is compatible to the spectrum analyzers, where you can directly capture your emissions you try to arrest. So just to give a thought for why EMI/MC, Tata has an advanced facility in Bangalore where they do EMI/MC measurement testings. For per day to do the measurement testing, per hour slot is 45,000. So that's the cost of EMI/MC today. But that will become a very effective, and it will give a certification along with that, such that our products are EMI/MC compatible. That's one thing with this. And one more thing, if we are into radars, now radars are not into only defense and other segments. Radars are also into mobility, which is basically our radar switcher and all those things which comes here, right? So there you are, now you are going to use the radar technology there. So radar works on pulse signals. So there is a signal generator also here, which is a very compact form factor. I'll just see, I'll show that. Yeah, these are the signal generators and analyzers I've been discussing. So this is basically a handheld product that is also compatible to do both CE and RE measurements here. And we have our benchtop solution also. And one more interesting solution is this. So any idea on what is this? The 6. That's a VNA. So that's a vector network analyzer. So you can see the form factor, how compact it is. It is like less than 3 kg. So, but it's a very high precision equipment which can do all your IMD measurements and other things also. No, this is not what we supplied. We supplied a benchtop equipment. Yeah. So this is a very compact equipment to characterize your materials and other things. Basically, this can go till up to 54 gigahertz. Yeah, there are multiple bands in between, but that can go till up to 54 gigahertz. That particular streamline series VNA.
So material analysis.
Material measurement comes with a separate software for it that has to be procured separately, but that software is also compatible with this series of VNA. So this is primarily to do characterization of your duty. Like say if you are manufacturing an antenna, if you are going to test an antenna, to characterize it, you are going to do it. Yeah, yeah, primarily antennas. Yeah. And to
What I am thinking, machine related flux analysis. Where do you
yeah.
flux analysis?
No, flux is like
Flux is
no. Basically, your respective of frequency, this starts from kilohertz, and few VNC start from in megahertz also. No, it depends on the VNA series which you are going to trick.
starts with megahertz.
I think yeah, that will be in 1 megahertz. I guess so. Yeah. Yeah, that is up to 54 gigahertz. What we are supplied now is. Yeah.
I requested to not to 100.
Yeah, in that band we don't have. From a lower to a higher side we don't have, but on a narrow band we have.
There 100 kilohertz to 200 kilohertz.
Okay.
It is not possible.
Now that band we don't
So
have.
we went to impedance.
Okay. And signal generator is where you are going to generate your pulsed signal to integrate with your radar and transmit and receive, and that will help you in that applications. So this is a quick overview. Just we got a 10-minute slot here, so we just set up. Sorry.
EV sector.
Yeah, EV sector is basically high performance power supplies and this battery emulator which I shown, which is in different form. Yeah, chart test solution. Those are called Sign Lab solutions. There is a separate team working on Sign Lab solutions. Yeah.
That is also we are proposing.
Okay.
That proposal is also ready.
Maybe we didn't get any info. Maybe the other team would have got it. Yeah, we came here for the installation. Yeah, yeah, 3 equipments. It is done, sir. It is done. Yeah, both together. Yeah, yeah. Rajiv sir has called few people there. Okay. VNA yesterday we had completed. Today now impedance analyzer and other equipment is going on today. Yeah. They are doing the demo, I guess now. You know. So this is just a quick overview. Yeah, yeah, yeah. Okay, to give basic overview like with impedance, it is a very direct measurement there. We just have to enter a frequency and we have to just calibrate our text fixture, which is just open and short. That if we do directly, we can go for the measurements. No any complicated setup or anything is required. Thank you. Yeah.
Thank you, the team from Keysight. Okay, you can share your details if anyone wants any information from Keysight Technologies. Because faculty members will be writing the projects, research projects and all, if they want, they are interested in your equipments. Because we know Keysight about only oscilloscopes. Okay. So Keysight, we already seen the oscilloscopes and sources, power source, but you are into other domain also. Okay. You can share your card. Okay. Yes, yes. Thank you. Gautam, thank you. Thank you, Gautam. Now we will break for lunch. Then at 2 o'clock, once again, we'll assemble here. We have one more Professor Vinay Kumar from NIT Warangal. Okay, so he will going to tell about the drives control mainly. Okay, so afternoon session.